Welcome to the fractional calculus seminar. Today we have Professor E.Kaslik, who is a full professor at the Department of Computer Science of the West University of Timisoara, Romania. She earned her PhD in applied mathematics in 2006 at the University of Sorbonne, Paris Nord, Paris 13, through a joint degree program with the West University of Timisoara. She obtained her habilitation in mathematics in 2015. She has authored and co-authored over 100 peer-reviewed publications and serves as a member of the editorial board of several journals, including Fractional Calculus and Applied Analysis and Mathematics and Computers in Simulation. Her main research focuses on stability theory for order and delay differential systems and mathematical modeling in neurosciences. She also advises graduate students and collaborates widely across applied mathematics, dynamical systems, and computational science. We are very happy to have you here. Professor, you may please begin your talk.
Thank you very much for the kind introduction and also for the invitation to take part in this fractional calculus seminar series. So my talk will be about Prabhakar kernels in fractional dynamics, and actually my background, as you just mentioned, is instability theory for delay differential equations, but also for fractional differential equations. And while stability theory is well known for Caputo systems of differential equations, it is much less so for Prabhakar systems, where actually the kernels have extra parameters, and the Prabhakar kernel actually models richer relaxation and viscoelastic and dielectric phenomena. So actually my talk will have three parts. I will start with a reminder of Matignon stability theorem for systems of Caputo fractional differential equations. So basically Matignon's theorem is very well known. We have revisited it a few years back and proved it using Prabhakar functions and kernels, and actually found a small correction to be made in the original statement. Also, in the second part of the talk, I will extend Matignon's theorem to study the stability of linear systems of Prabhakar fractional differential equations, and I will show how this extension is done. And then during the third part of my talk, I will focus on fractional differential equations with two different Prabhakar derivatives. I will present explicit stability and instability conditions for such two-term equations, and also numerical schemes. Actually, these are implicit L1 and L2 time schemes, which are tailored for Prabhakar derivatives. And as a case study or as an extension, I will present a Duffing model with two Prabhakar derivatives and show how fractional parameters influence chaotic behavior and periodic behavior in such equations. Okay, so I will start with a little historical background. The Prabhakar function dates back to 1971, so this is more than 50 years already. It has been introduced by Indian mathematician Prabhakar, who studied convolution integral operator with a generalization of the Mehta function as a kernel. Actually, they have been overlooked mostly until the 2000 when connections to the Havriliak-Negami dielectric model has been discovered. And actually, operators which are based on such on the Prabhakar function are employed to describe in the time domain relaxation models in several areas, and I would like to refer to the works of Roberto Garappa and Mainardi, Maione, Giusti, and Colombaro, which are mentioned here in the slide. The definition of the Prabhakar function is presented here. So it is also called three-parameter Mehta-Leffler function. We have three parameters, alpha, beta, and gamma in the expression of the Prabhakar Prabhakar function. As some properties, I would mention that it is an entire function of order 1 over alpha and type sigma equals to 1. When the parameter gamma is equal to 1, the Prabhakar function reduces to the 2-parameter Mittag-Leffler function. We also have a derivative identity, which actually gives the derivatives of the 2-parameter Mittag-Leffler function in terms of the Prabhakar functions. And also, I mentioned here a useful integral identity, which we will use a bit later towards the end of this talk for our numerical scheme. Okay, the asymptotic properties of Prabhakar function play an important role in the stability results that I will present a bit later. They have been studied for large arguments in papers of Paris and again Roberto Gara, and so on. I would also like to emphasize this last paper, A Practical Guide to Prabhakar Fractional Calculus, which reviews a lot of results from the field. So the asymptotic properties can be expressed in this way as presented over here. We notice that we split the complex plane into several sectors based on the Stokes and anti-Stokes lines given by the absolute value of the argument being equal to alpha pi over 2 or alpha pi. Here we have an exponential expansion denoted by E and algebraic expansion denoted by A in the formulas above. And please notice that the first term also always represents the leading term. So as a graph, maybe it's easier to talk about it like this. We notice that in this region, the exponential term is the leading one. It is a large exponential term. And when we move across the anti-Stokes line, the algebraic term becomes dominant and the exponential term becomes small, and it vanishes once we cross the Stokes line in this region. Continuing with the Prabhakar kernel, the Prabhakar kernel is defined as t to the power beta minus 1 multiplied by the Prabhakar function of coefficients alpha, beta, and gamma computed at t at alpha multiplied by a complex lambda. The nice property of the Prabhakar kernel E presented here is that it has an analytical representation for its Laplace transform, which is not true for the Prabhakar function itself. And the Laplace transform is given by this formula for real of S positive and absolute value of S larger than the absolute value of lambda to the power of 1 over alpha. Now, from the asymptotic properties of the Prabhakar function, we can deduce the asymptotic behavior of the Prabhakar kernel as well, which is presented over here. Again, we can notice that actually the asymptotic behavior changes once we cross the wedge absolute value of the argument equals to alpha pi over 2. Also, it is very important to mention that Prabhakar kernel is completely monotonic, and this is important in the case when it is used to model relaxation phenomena. So our Prabhakar kernel is completely monotonic if the following conditions hold. So lambda is smaller than 0, alpha is between 0 and 1, and alpha, gamma are positive, and their product is smaller than beta, which is smaller than 1. I will keep coming back to the complete monotonicity conditions because most of the results that I will present in this talk will be obtained in this setting. Okay, now we have here the definition of the Prabhakar derivative and the Prabhakar integral. So from now on, we assume that alpha, beta are positive, gamma is real, and omega is negative. The fractional Prabhakar integral of a function f from L1 is defined as the convolution of the Prabhakar kernel with the function itself. And then for beta between 0 and 1 and the function f absolutely continuous, The inverse operator of the Prabhakar integral operator, regularized in Caputo's sense, is given below. So here we have the convolution of this Prabhakar kernel with the coefficients alpha, 1 minus beta and minus gamma, and the derivative of the function. This can be extended for the generalized regularized Prabhakar derivative, again in the Caputo sense, in the case when the coefficient beta is not necessarily between 0 and 1. I would like to mention that focusing on the fractional Prabhakar derivative, if either omega tends to 0 or the coefficient gamma tends to 0, this converges towards the Caputo derivative of order beta. Okay, so I have arrived to the first part of the talk after this small introduction. So I will present the proof of Matignon's theorem based on the Prabhakar kernel. We start with a general n-dimensional fractional order system with Caputo derivatives presented by this system 1 here. Q is a multi-order coefficient. The orders are from 0 and 1, and actually the Caputo derivative of order Q means the element-wise application of the derivative of orders Q1, Q2, and so on to the components of the function Y. For the existence and uniqueness of the solution of such fractional order systems, when the function f from the right-hand side is continuous and Lipschitz continuous with respect to the second variable, I would like to refer to the work of Diethelm, Sigmund, and Tuan. All right, so if we denote by phi of t and y0 the unique solution of the previous system, which satisfies the initial condition y of 0 equals to y0, then we have the usual stability and asymptotic stability concepts as in the integer order case. But we also have the concept which is characteristic for fractional order systems. The trivial solution, or our system, is called asymptotically stable of order t to the power minus alpha if it is stable and there exists rho positive such that for any initial condition starting in a ball of radius rho, we have that phi of t and y0, so our solution converges to 0 as t approaches infinity, but of order t to the power minus alpha. So this is important from the point of view of fractional systems, because convergence is not going to be exponential, but it is going to be algebraic. Okay, so for single order linear systems of fractional differential equations, here I repeat to Caputo fractional order differential equations. We consider the matrix A for this system, and the characteristic equation which is associated to our system is this simple one, the determinant of S to the power Q times the identity matrix minus A equals to 0. And by basic means, we can actually show that our system 2 is asymptotically stable if and only if the spectrum of the matrix A avoids the image of the power function S to the power Q for the real part of S larger than 0. Now, this is not so easy to verify in all cases. So I would like to go back to the initial statement of Matignon's theorem from 1996, which has become a classical result since then. Which actually says that our linear system is going to be asymptotically stable of order t to the power minus q, so it decays as t to the power minus q, if and only if the spectrum of the right-hand side matrix is included in this wedge of the complex plane, so the absolute value of the argument of lambda is larger than q pi over 2. Matignon's theorem has a second point as well, which says that in the limit limiting case, so our system is stable if and only if the spectrum is included in the closure of the above set defined, and the eigenvalues of our matrix A, which are exactly on the boundary of the stability region, so they satisfy that the absolute value of the argument is equal to Q pi over 2, have geometric multiplicity of 1. We were looking at the proof of this theorem with my colleague Juana Brandibur and Roberto Garapa, and we actually built up the proof using basic means, using the Jordan normal form decomposition for the matrix A of our system. So assuming that J is the Jordan normal form of the matrix A with the blocks J1, J2, Jp. Okay, these are Jordan blocks corresponding to eigenvalues lambda k of the matrix. Then, just as a reminder, the index of an eigenvalue lambda k is the size of the largest Jordan block jk associated to the eigenvalue, where the geometric multiplicity represents the total number of Jordan blocks which are associated to the eigenvalue in the Jordan normal form. Actually, we have noticed that in the limiting case, Matignon's result does not hold if we use geometric multiplicity. Instead, we have to replace geometric multiplicity by index. So in the limiting case, when we have eigenvalues of the matrix A on the boundary of the stability domain SQ defined here, they need to have index 1 for the system to be stable. The proof of the theorem is included in our paper from 2021. I will just present a short outline of the proof because it connects to the Prabhakar kernel, and it is the basis of everything that we are doing afterwards. So the idea roughly is the following. We just transform our system into an equivalent system, but for which we have the Jordan normal form of the matrix A as the matrix. We apply the Laplace transform to this linear system, and we obtain the solution in the Laplace domain. And we notice that the matrix SQ times the identity minus J to the power minus I has to be block diagonal, because J is obviously block diagonal, and the blocks of this inverse matrix are actually it can be actually written in this way, where we have upper triangular matrices here. The dimension dk, very importantly, the dimension dk of such upper triangular matrices represents the dimension of the kth Jordan block jk, which is associated to some eigenvalue lambda k here. So why is this important? Because once we have this triangular matrix, we can see that the solution in the Laplace domain for our system is made up of blocks. Each of the blocks have size dk, which are of the following form: zk of s presented here. And what we notice over here is that we have obtained Laplace transforms for the Prabhakar kernels in this expression of the blocks of the solution in Laplace domain. So when we apply the inverse Laplace transform, the corresponding block solution block for the solution of our system in Jordan normal form can be written in this way, where obviously the Prabhakar kernels appear with the coefficients alpha equals q, beta equals to, in general, j minus 1, k plus 1, and gamma is actually j or positive integer. So looking at the Prabhakar kernels, which appear here in the formula of the solution, and using the asymptotic properties that I have presented in the introduction, actually we can see that these Prabhakar kernels that appear here have the following asymptotic expansions as t goes to infinity. And so based on these asymptotic expansions, we can very simply obtain the conclusions from Matignon's theorem. So basically when the argument of lambda in absolute value is larger than q pi by 2, we can see very easily that t to the power minus q here tends to 0. So our solution, our null solution, is going to be asymptotically stable. However, if we are in this region and we have strict inequality, because of the exponential terms, the solution is going to be unbounded, so it cannot have stability. On the other hand, when we are exactly in the limiting case, so when the absolute value of the argument is equal to q pi over 2, the behavior of our solution will be given by these terms t to the power m minus 1, because the exponential is going to be bounded. So we can get bounded behavior if and only if m is equal to 1, which returning to the previous formula for the kth block of the solution means that actually the kth block has to be one-dimensional. So this dk has to be equal to 1. And this actually reduces to the fact that if we have an eigenvalue lambda for the matrix A, which satisfies this limit condition, argument of lambda in absolute value equals to q pi by 2, the solutions are going to be bounded if and only if the size of the largest Jordan block associated to this critical eigenvalue will be equal to 1. And this actually means that the index of the eigenvalue has to be equal to 1, not necessarily its geometric multiplicity. And as an example, I would like to present some numerical simulations that we have done to verify our theory. So in the first example, actually in both examples, we have considered 4-dimensional systems. In the first example, the matrix is given right here and the corresponding Jordan normal form. We actually notice that we have two eigenvalues. Each of them have Jordan blocks of size 2. And actually for each of the eigenvalues, we only have one Jordan block. So it means that the index is going to be 2 and the geometric multiplicity is going to be 1. Now, considering q equals to 2 over 3, we actually notice that we are exactly in the limiting case. So the argument of both eigenvalues is equal to plus or minus q pi by 2. And based on the numerical simulations that we see over here, indeed, the solution which originates close to the origin will grow indefinitely. Here, the solution has been computed by direct evaluation of the matrix Mehta function, which is presented over here, and which actually gives us the solution to our Caputo fractional order system. In the second case, we have considered a modification of the previous matrix. So now the matrix A2 of the system is shown here with the corresponding Jordan normal form. Actually, the eigenvalues are the same. However, what happens is that their geometric multiplicity is 2. We have exactly 2 Jordan normal blocks corresponding to each Jordan blocks corresponding to each of the eigenvalues. But their size is 1, so the index of the eigenvalues is going to be equal to 1. And what we can see is that we get bounded oscillations and the origin is stable in this case. So these two numerical examples verify our findings that in the original statement of Matignon's theorem, we have to replace geometric multiplicity by index equals to 1. Now, for the second part of my talk, I will present some results about the stability of linear systems of Prabhakar fractional differential equations And basically, the previous part is a good motivation for this study. So our question was how to extend Matignon's results for Caputo systems of fractional differential equations to systems of fractional differential equations, but with Prabhakar derivatives. Please note that in system 4, we have the same Prabhakar derivative applied in each of the differential equations, and we assume that that our Prabhakar kernel is completely monotonic, so these inequalities hold. It is important to note that our system is equivalent to a system of weakly singular convolution type Volterra integral equations, which is presented over here. Y0 is just the initial condition associated to the system. This is a joint work with Roberto Garapa that we have published a few years ago. So this time, the characteristic equation which is associated to the Prabhakar system is this one. It looks more complicated than in the Caputo case, obviously, because of the parameters, the extra parameters that we have in the Prabhakar kernel. We can notice that our equation can be decomposed as this equation here, where lambda is one of the eigenvalues of the matrix A. So we obtain the following result. The linear system with Prabhakar derivative is asymptotically stable if and only if the spectrum of the matrix, the set of its eigenvalues, is not in the image of this function when S has positive real part. So the result is more complicated than in the Caputo sense, but what we wanted to do is to characterize this stability region that we denote by S, alpha, beta, gamma, and omega in the complex plane. And for this, we have used the root locus method. So this is based on the fact that for the characteristic equation, we look for roots on the imaginary axis. We have found that the boundary of the stability region can be characterized by a curve defined by a parametric equation, and the parametric equation involves this function lambda defined on 0 alpha pi by 2 with complex values. It is presented here, and it has the following properties. As theta tends to 0, our lambda converges to either 0 or the absolute value of omega to gamma in the limit case when beta minus alpha gamma is 0. And as theta converges to alpha pi by 2, the absolute value of the lambda function grows to infinity. Also, a very important property is that the argument of lambda of theta is going to be between 0 and beta pi over 2. And then using this function lambda, we can define the curve psi of parameters alpha, beta, gamma, and omega parametrically using the function lambda defined above. And it is important to note that this curve is simple and it is included in the first quadrant of the complex plane. So this is going to give us the boundary, actually this and its conjugate is going to give us the boundary of the stability region in the Prabhakar case. Mainly, we have obtained the following stability theorem. The stability region of our Prabhakar system is bounded by the curve psi and its complex conjugate. It is important to note that for the standard Caputo derivative of order beta, so when we make the parameter gamma converge to 0, the curve psi approaches the Hoff-line argument of lambda equals beta pi over 2 in the complex plane, and so we recover the stability region from Matignon's theorem, the one that we have already reminded. Here is a short proof that I will actually skip this time. But I would like to present a few graphs of the stability region that we have found. So here, alpha, beta, and omega are fixed for each of the figures, and we consider increasing values of gamma. So here, gamma is 0.1, then 0.8, and so on. Actually, the 0.1 case is the closest to the Caputo case, to the Caputo wedge. And we notice that as we increase gamma, also still with the complete monotonicity conditions holding, we get larger and larger domains, and the boundary of the stability region becomes more curved. The last figure here actually is for the special case when beta minus alpha gamma is equal to 0. Finally, I would like to present the same or similar stability regions, but this time alpha, beta, and gamma are fixed, and omega decreases from minus 0.1 to minus 2. And we can also see that as omega decreases, the stability region, the corresponding stability region, the blue region here, decreases. The dark blue curve represents obviously the boundary. Okay, now I would like to talk a little bit about the numerical solution for the Prabhakar fractional differential equations that we have developed in this paper as well. So the point was that we wanted to verify our theoretical findings, and since the analytical solutions are not available in this case in a simple or closed form, we actually used two approaches. One approach was to derive asymptotic representations for the exact solution for small and large arguments, and also to develop a convolution quadrature method for problems with a fractional Prabhakar derivative. So I will refer here to the scalar case only. This generalizes easily to the vector case as well. So for the asymptotic expansion for small arguments, actually things are quite standard. We rewrite our equation in the Laplace domain in this form, and we consider the transfer function from the Laplace domain that we can represent this way. And then for large values of the absolute value of S, we can represent the transfer function as this series. And again, we can recognize that what we have here are Laplace transforms of Prabhakar kernels. So inverting back each term from the series, we obtain this asymptotic expansion for our solution for small arguments. For large arguments, things are a bit more difficult, because now for the transfer function, we also have to take into account the singularity. We can prove theoretically that there exists only one singularity, and this is eliminated using standard residue subtraction. Here for the computation of the residue, we actually use this formula that can be obtained by simple derivations. And then again, we expand the transfer function h of s for sufficiently small values of the absolute value of s in this way. And finally, transforming back to the time domain, we are able to obtain the asymptotic expansion for our solution as t goes to infinity. For the numerical solution, we have devised a method for solving general nonlinear systems with the Prabhakar derivative. Starting from the trapezoidal rule that is generalized in the framework devised by Lubitsch. The generating function that we consider is delta of xi, considered here, and our trapezoidal convolution quadrature rule, which is devised for system 5, is represented by this scheme over here, where the W's represent the starting weights and Cn represent convolution weights. Now the convolution weights are actually found from the asymptotic expansion of the function g, the function g being the Laplace transform of the Prabhakar kernel, but which is applied to our generating function delta divided by the step size. This can be evaluated with high accuracy by Cauchy integration, and the starting weights are introduced in the numerical scheme to handle the lack of smoothness at the origin of the solution. And they are evaluated by imposing that we have exact solutions for functions of the form t to the power nu, where nu is a multiple of beta but less than 1. Now, for the numerical experiments that we have done, we have two examples, a linear one and a nonlinear one. So starting with a simple linear scalar example, we compute the solution of this linear equation where the coefficient a can be complex. So we have three situations that we have chosen. Alpha, beta, gamma, and omega are fixed to these values which are given over here, and we are close to the stability boundary. So actually we choose three separate values for the coefficient a, a1, a2, and a3. a1 is just inside the stability region, a2 is exactly on the boundary, and a3 is just outside the stability region that we have determined theoretically. So these are the evolutions that we actually obtain for the three cases. So in the first case, when we are inside the stability region, we can see that the solution converges to 0. We have also checked what happens for t large, and actually we can say that the asymptotic expansion overlaps with the result provided by the numerical method. So this shows the reliability of the numerical method. Then in the second case, when we are exactly on the boundary of the stability region, we can observe that we obtain persistent oscillations, while for the third case, when we are just outside the stability region, our solution presents increasing oscillations and diverges. For the second numerical experiment, we have considered the Brusselator model. So this is just a toy model where the integer order derivatives have been replaced by the same Prabhakar derivative. It is important to note that this system has an equilibrium at 1 and b over a. These are the eigenvalues of the Jacobi matrix evaluated at the equilibrium point. And if we consider the coefficients to be a equals to 10 and b equals to 14, we have these corresponding eigenvalues. And now obviously, depending on the choice of the parameters alpha, beta, gamma, and omega of the Prabhakar derivative, these eigenvalues can be inside or outside the corresponding stability region. And this is what we have tested in the numerical simulations. So in the first case, for actually alpha, beta, and gamma have the same values for both cases. We have just modified omega from -4 in the first case to -0.5 in the second case. So in the first case, the eigenvalues of the Jacobi matrix are inside the stability region presented here, while in the second case, λ1 and λ2 are outside the stability region. And the numerical simulations show that in the first case, the solution converges towards the asymptotically stable equilibrium, while in the second case, we have persistent oscillations that appear. And actually, we can compute based on the formula that we have for the lambda function given by our root locus method, we can obtain the exact critical value of omega, which is -1.5 in this case, for which the eigenvalues will belong to the boundary of the stability region. And we conjecture that at this value, a Hopf-type bifurcation takes place, which causes the appearance of oscillations. Okay, so this was the second part of the talk, which refers to systems with the same Prabhakar derivative. So as an extension to this, we were wondering, okay, but what happens to multi-term equations with Prabhakar derivatives? And the simplest extension is to see how we can establish stability conditions for differential equations involving two Prabhakar derivatives. Okay, so we have considered an equation with two Prabhakar derivatives as described by equation 7. Again, we still have the complete monotonicity conditions in this setting. So omega is negative, both gamma parameters are positive, alpha and beta are between 0 and 1. And we have ordered these differences, beta 1 minus alpha gamma 1 larger than beta 2 minus alpha gamma 2, and both of them are positive. Now, again, we have similar stability concepts as before. I will not insist on this. The characteristic function which is associated to our linear equation with two Prabhakar derivatives is the function delta presented here, which again is quite complicated. It involves power functions, complex power functions, a lot of parameters appearing here because of the two Prabhakar derivatives. In what follows, we have denoted by delta 1 the difference beta 1 minus alpha gamma 1, and delta 2 is beta 2 minus alpha gamma 2. And based on our assumption, delta 1 is larger than delta 2. And our first result, which we obtained by analyzing the distribution of the roots of the characteristic function, is that the equation with two Prabhakar derivatives is globally asymptotically stable of order t to the power minus delta 2, if and only if all the roots of the function delta are in the open left half plane. Otherwise, if b is not equal to 0, so the free term here, then delta has a root in the open right half plane, and delta has a root in the open right half plane, then the equation is unstable. So in order to, again, to characterize the stability and instability regions respectively, we have looked a bit further to this analysis of the distribution of the roots. And we have obtained some fractional order independent and dependent stability results first. If we look at the following cases, so if beta is negative, we can prove that our equation is unstable regardless of the fractional orders. While if A and B are in the first quadrant of the AB plane, the equation is asymptotically stable, again, for any choice of the fractional orders of the Prabhakar derivatives. We have also obtained the fractional order dependent results in this way. Actually, if this simple inequality holds, we can show that the equation is unstable, while if A is smaller than 0 and smaller than B, a boundary curve gamma in the AB plane will arise from pure imaginary roots of delta S by the root locus method, and can be parametrized in this way: lambda of theta equals to A of theta and B of theta. I will just give the formulas in the next slide, which separates the stability and instability regions respectively. I will show the graphs for these plots just in a minute. So the functions A of theta and B of theta, the components of the function lambda, which gives us the stability boundary, are expressed by the equation 8. Their formulas are not very simple, but we can deduce that they are C infinity functions, and they satisfy the following limits at 0 and alpha pi by 2. And also the image of the function lambda in the AB plane defined by the parametric equations above is a curve gamma, which is included in the second quadrant of the AB plane. So in this case, the stability boundary is in the second quadrant. So the main fractional order dependent result that we have obtained is that if we consider the curve gamma parametrically defined before, our equation is going to be asymptotically stable of order t to the power minus delta 2, if and only if the parameters a, b, the coefficients of our equation, belong to the region above the curve gamma, while if they are below the curve gamma, the equation will be unstable. So these are the plots for our stability regions. You can see two colors, red and blue. Actually, dark red represents the fractional order independent stability region. So if we pick the coefficients a and b inside the first quadrant, the equation is going to be asymptotically stable for any Prabhakar derivatives that we would take into account. The lighter region here represents the fractional order dependent stability region. The curve here represents in each of the graph the stability boundary, and then the blue region represents the instability region. Darker again refers to fractional order independent instability region, while light blue represents the fractional order dependent instability region, respectively. So what we can see, as I said at the very beginning, when B is negative, the trivial solution is going to be unstable for any choice of the Prabhakar derivatives. So actually, it is just the second quadrant where things become a bit more complicated, and we will have dependence on the choice of the Prabhakar derivatives in our equation. So again, in order to test our results, we have devised a numerical example that I presented over here. We have these two Prabhakar derivatives involved. The values of the coefficients are given below. We have also introduced a nonlinear term just for the sake of the numerical example. So we notice that for these fixed values of the parameters, the critical value of the A coefficient that we can determine from the theoretical results that we have found is minus 0.93. So values of A below this value of A star give rise to unbounded oscillations. The null equilibrium is unstable, while values of A above the value of A star make the solution converge to the null solution, as we can see from the graphs. And as an extension to this, actually, since we are dealing with two-term Prabhakar differential equations, we were thinking what would happen if we applied the theoretical results to, or we wanted to extend actually the theoretical results to Duffing type of oscillator. And in this case, basically, we cannot fully rely on the theoretical results that we have obtained, because in the first term, in the first Prabhakar term, we would like to have a fractional acceleration. So the complete monotonicity conditions are not going to hold anymore. The coefficient beta 1 is chosen to be between 1 and 2. So here, the first term, as I said, represents a fractional acceleration. The second term represents fractional damping. And then we have, as usual, the linear stiffness, the nonlinear stiffness, and the forcing term on the right-hand side. So what happens in this case? We cannot fully make use of the stability results that we have determined in the complete monotonicity when taking into account the complete monotonicity conditions. In the Duffing oscillator, we set beta 1 to belong to 1 2 to the interval 1, 2. And in this way, the Prabhakar derivative will act on the second order derivative of y and represents a fractional acceleration, while, but actually in this case, still the Caputo-Prabhakar operator is well defined, but we don't have the complete monotonicity conditions anymore. The implications of this is that, yes, we can still take into account some of the theoretical results. The curve gamma that I have showed before remains a practical guide for the boundary of the stability region, but actually for our stability analysis, the full complete monotonicity free analysis is ongoing. So for the numerical scheme, we have come up with an L1, L2 type scheme. So for the first Prabhakar derivative, for which the order beta 1 is between 1 and 2, we use an L2 type scheme with a simple quadratic start here. Between 0 and T1, we approximate the second order derivative by this difference, which involves the first order derivative computed at 0. We use the kernel identity, which is a property of the Prabhakar function that I mentioned at the very beginning. And in this way, we can find a numerical approximation for the Prabhakar derivative computed at the first moment of time t1. We use the following kernel weights, which are presented here. They can be pre-computed once and then used in the numerical scheme. Then for the second step of our L2 scheme, we just split the interval from 0 to T1 and from T1 to T2. And on the second interval, we just use the second order difference for the approximation of the second order derivative. And in this case, again, after applying the kernel identity, we obtain the approximation of the Prabhakar derivative at T2. And we continue this obviously for the next time steps. And finally, we obtain the following closed form for the approximation of the Prabhakar derivative with order beta 1 larger, I mean between 1 and 2. Again, these are the weights that are involved. For the second Prabhakar derivative, since beta 2 is between 0 and 1, we just devise the simple L1 piecewise linear discretization, considering again uniform step sizes. And again, using the kernel identity, we find a closed form for the approximation of the Prabhakar derivative at the time step tk, where now the weights are given over here. Okay, so finally, I'm sorry. Yeah, so finally, when we just replace in our Duffing model the Prabhakar derivatives by their approximation, this leads to an implicit scalar equation of this form that we solve actually at every step, but by a Newton-Raphson solver. The initial conditions that we have considered are 1 and 0 respectively for the function and its derivative. These are usually initial conditions which are associated to the Duffing model. So let me show you, okay, some remarks first. Actually, you in the formula for the weights, we have the Prabhakar function appearing. So for the evaluation of the Prabhakar function, we have used the optimal parabolic contour Laplace inversion, which has been presented in some papers of Roberto Garappa and Maione. Here we choose the contour parameters to balance the truncation and round-off errors and to avoid the Laplace transformed singularities. As for the convergence of the numerical scheme, well, again, the study is ongoing. If, for instance, the Prabhakar derivatives would be replaced by Caputo derivatives for the L1 scheme on a uniform mesh, we would have order of convergence delta T2 2 minus beta 2 for smooth data. If we have non-smooth initial layers, of course, this rate of convergence would be reduced. We could use graded meshes or corrected starts. For the Prabhakar derivative, the L1 scheme is first order on a uniform grid. However, for the L2 type part, where beta 1 is between 1 and 2, if the Prabhakar derivatives were replaced by Caputo ones, by the simpler Caputo ones, actually we could get higher order variants with near second order accuracy. However, our Prabhakar L2 type discretization is empirically first order. Okay, so as for the numerical simulations, when we vary gamma 1 and gamma 2, we observe that these are the shape parameters which are associated to our Prabhakar kernels. So we note that for increasing values of gamma, there's a qualitative change in the nature of the attractor of the Duffing oscillator. The first plot over here corresponds mostly to what happens in the integer order case, when the gamma parameters are close to 0. Please note also that beta 1 is close to 2 and beta 2 is close to 1 in these simulations. So in the classical integer order case, we would have this double scroll chaotic attractor, and we notice that actually as we increase gamma 2, the complexity reduces and we just get some periodic oscillations. This can also actually this is the same case when we vary gamma 1 and gamma 2, but we start with a case where for the integer order Duffing oscillator we have a periodic solution. We can actually get even chaotic behaviors for increasing values of gamma 2, while when gamma 1 is increased, actually for larger values of gamma 1, we get periodic solutions with smaller periods. Finally, what we have noticed that when we vary the parameters beta 1 and beta 2, not much change is observed. So again, here we started from the double scroll attractor, which is associated to the integer order classical Duffing model. And yes, qualitatively, the dynamics haven't changed even for much smaller values of beta 2 and beta 1. Now, with respect to omega, what we notice is that if for omega minus 0.5, we have a double scroll chaotic attractor, when we decrease omega, this may switch to a period 4 attractor, then to a period 2 attractor, and finally to a period 1 attractor to our system. So it seems that omega modulates the complex behavior of the Duffing oscillator. Okay, so some conclusions and some future work which is ongoing. So in this third part, which is maybe the most recent study that we have undertaken, we have presented the stability map for linear two-term fractional differential equations with Prabhakar derivatives. We have obtained the explicit stability boundary in the plane of coefficients A and B. We have obtained fractional order independent and dependent stability facts, but taking into account complete monotonicity conditions. Now, what is ongoing, we are trying to extend this stability theory for the case also when beta 1 is larger than 1. From the numerics point of view, we have devised an implicit L1, L2 scheme with some pre-computed weights, which are expressed in terms of Prabhakar functions. This reaches first order time accuracy, at least empirically, and what we can do next, we want to devise higher order methods using convolution quadrature with startup corrections, and acceleration could be reached using the sum of exponential method or the fast Fourier transform. For the Duffing oscillator, we have seen that the memory shape parameters gamma and omega affect the behavior of the system, and they can steer the system from chaotic to periodic behavior, while the parameter beta, which is possibly the main fractional parameter, does not induce very important qualitative changes. And what is ongoing at this moment is the computation of Lyapunov exponents for the Duffing model using a two-trajectory method with renormalization. So this would be it. I would like to thank my collaborators, Roberto Garapa, Juana Brandibur, and Aman Jinga, with whom I have been working on these topics. And thank you very much for your attention.
Thanks, Eva, for the nice talk. For questions, please raise your hands. I'll call out your name in the order they appear on my screen.
Question, please.
Yes, please go ahead.
Yeah. Oh, thank you for your interesting talk. Can you open the page 44?
44, yeah, sure.
Yeah,
I'll go back. I'll go back. Yeah, sure. Here, yeah. The model, the Duffing model. This one?
Yeah, Duffing model. Yeah, that's it. Can you say me in here the exact meanings of the parameter fractional Prabhakar fractional derivatives?
So
For example,
here actually,
gamma 1.
yeah. So actually, for the fractional orders, so what we did here is what we were just playing with the Duffing oscillator model, because since we were studying two-term differential equations with two separate Prabhakar terms, it seemed like a good example to try to see how our theory will suit the modeling example. So the first term here would correspond to the second order derivative in the traditional model. It represents a fractional acceleration. It would represent a fractional acceleration. Then the second term would be a fractional damping term. And finally, the other terms are not modified, the linear and nonlinear stiffness and the forcing term respectively. Now for the coefficients, if you want, the gamma coefficients in the Prabhakar derivatives are related to the shape of it's sort of memory shape. Beta 1 and beta 2 are the main, I see them as the main fractional orders, because what happens is that when gamma 1 or omega go to 0, the Prabhakar derivatives converge to the Caputo derivatives of order beta, respectively. And the alpha orders here, the alpha orders are just some time shaping parameters, because they appear as t to the power alpha in the Prabhakar kernel, or s to the power alpha in its Laplace transform. So we don't. So at this point, we do not pretend to, to be able to describe phenomenologically with Prabhakar derivatives in a better way viscoelastic properties in such an oscillator, but we were just playing with the model.
Yeah. Did you find this equation's solution, the 9 equation?
I'm sorry. Can you? I think I have a problem with.
Can you solve? Can you find this equation solution?
No. Actually, we have seen. Yeah, we have seen some papers with the Duffing oscillator, but with Caputo derivatives.
Thank you very much.
Yeah. Thank you very much for the question.
Are there more questions? You can unmute your mic. I guess there are no further questions. So this is a good point to stop this talk here. Thank you very much for the nice talk.
Thank you very much again for the invitation and for the opportunity to give you the talk in the seminar. And also thank you everyone for attending.
Yes, it was our pleasure. Thank you very much.